Welcome to more implicit differentiation examples. So for this example, use implicit differentiation to find y prime if sine of y plus y cubed equals cosine of x plus x. So once again, the very first thing we should do is we should go ahead and differentiate both sides with respect to x. So on the left-hand side, we will take the derivative with respect to x of sine of y plus y cubed. And then on the right-hand side, we will take the derivative with respect to x of cosine of x plus x. From this, we can go ahead and split each of these if we want, or we can, so this becomes the derivative with respect to x of sine of y plus the derivative with respect to x of y cubed equals the derivative with respect to x of cosine x plus the derivative with respect to x of x. On the left-hand side, we're going to be using the chain rule. On the left, on the right-hand side, we will just differentiate with respect to x. So on the left-hand side, we're going to take, let me give myself more room. Okay. Again, on the left-hand side, the chain rule, we're going to turn this into taking the derivative with respect to y of sine of y. And then that becomes multiplying by the derivative of y with respect to x. Then to that we will add, again, we are going to take the derivative with respect to y now of y cubed. Multiply by the derivative of y with respect to x. And then on the right-hand side, we just have our standard derivatives. So the derivative of cosine x is negative sine of x. And the derivative of x is just 1, so we have plus 1. From here, we can go ahead and take the derivative with respect to y. So the derivative of sine of y is cosine of y. Again, that's multiplying dy dx. And then the derivative of y cubed with respect to y will be 3y squared by the power rule. Again, multiplying dy dx. And this is all equal to negative sine of x plus 1. At this point, we're done differentiating. Now we simply need to solve for dy dx. So we can go ahead and factor a dy dx out of that left-hand side. So we have dy dx factored out front times cosine of y plus 3y squared is equal to negative sine of x plus 1. From here, we can go ahead then and divide by our cosine of y plus 3y squared. And we wind up getting dy dx is equal to negative sine of x plus 1 all over cosine of y plus 3y squared. Again, dy dx is an alternative notation for y prime. So this is also what y prime equals. I recommend using dy dx's instead of writing y primes as you do implicit differentiation, just because it's easy for y prime to suddenly morph into y if you think that the prime symbol is just a dot that you accidentally wrote. So using dy dx, it's very clear that that is the derivative of y. So that is the first example. Let's go ahead and take one more example. And let's go ahead and use implicit differentiation to find y prime if we have x cubed plus y squared, all in parentheses raised to the 5th, is equal to x plus y. So again, we're going to differentiate both sides with respect to x. So we want to take the derivative d dx of x cubed plus y squared, the whole thing raised to the 5th, and that is equal to the derivative with respect to x of x plus y. From here, we have a chain rule on the left-hand side, or a generalized power rule. The outside function is raising to the 5th. So this will become 5 times x cubed plus y squared raised to the 4th. And then we should multiply by the derivative of x cubed plus y squared. Again, this is acting like my u. So this is taking the derivative of u to the 5th would be 5u to the 4th. And then we're taking the derivative of u. And on the right-hand side, this becomes the derivative with respect to x of x plus the derivative with respect to x of y. From here, we need to differentiate the x cubed plus y squared. Oh. And put this back in the other color. So this was x cubed plus y squared. And if we differentiate that, we now have 5 times x cubed plus y squared raised to the 4th power times the derivative of x cubed with respect to x is 3x squared. Then we are going to need to take a derivative with respect to y of y squared. And then multiply that by dy dx. And then on the right-hand side, the derivative of x is just 1, and the derivative of y with respect to x is just dy dx. Oh, I'm missing a parenthesis on the left-hand side. There we go. From here, again, we have our 5 times x cubed plus y squared raised to the 4th power times 3x squared plus 2y dy dx is equal to 1 plus dy dx. At this point, we need to solve for dy dx. So we will have to do some multiplying out and then rearranging and then some factoring. So if we multiply in our 5 times x cubed plus y squared to the 4th power, since we have a dy dx inside that set of parentheses, we have 5 times x cubed plus y squared raised to the 4th power times 3x squared actually becomes 15 times that times x squared. So we have 15x cubed plus y squared raised to the 4th times x squared. And then factoring in the next becomes 10 times x cubed plus y squared raised to the 4th power times y times dy dx. And this is equal to 1 plus dy dx. Then we're going to rearrange. Let's put all the dy dx's on the left and all of the things without dy dx on the right. So we'll go ahead and subtract both dy dx from both sides. And we'll add our 15x cubed plus y squared to the 4th power times x squared to both sides. And what we are left with on the left-hand side, we have 10y times x cubed plus y squared raised to the 4th power copies minus 1 copy of dy dx. And on the right, we have 1 minus 15x squared times x cubed plus y squared raised to the 4th power. At this point, we can go ahead and divide by our 10y x cubed plus y squared raised to the 4th power minus 1 on both sides. And we wind up with dy dx is equal to 1 minus 15x squared times x cubed plus y squared, all raised to the 4th power, divided by 10y times x cubed plus y squared raised to the 4th power minus 1. So these answers can be semi-complicated in the end. They are in terms of both x and y. But this process at least allows us to find the derivative of y with respect to x.